Hi everyone, my name is Evgenii. My talk is going to be about enhancing model checking and Lincheck with partial order reduction. So this is the rough plan of the talk. I'm going to give a brief overview of Lincheck for those who haven't heard about it. Then I'm going to quickly describe what is model checking and what is partial order reduction. Then I'm gonna present the algorithm we've been developing for Lincheck. I also want to touch some of the technical challenges that we encountered when we were integrating the algorithm into Lincheck. And finally, I'll give some roadmap for future work we are planning with respect to this. Okay, so Lincheck is a declarative framework for testing concurrent algorithms on the JVM. It's developed by our small team at JetBrains. It is an open source library, so you can just download it and start using. So let's have a look at how it works. So suppose you are developing some concurrent algorithm or concurrent data structure or whatever, some concurrent code. And usually it's much harder to test concurrent code compared to sequential because like essentially the concurrent execution is non-deterministic. So you need at least some kind of stress testing to run the algorithm multiple times to see what possible different outcomes are possible. And the Lincheck, it essentially automates this routine for you. So you don't need to write any setup for your stress tests or whatever. You just need to specify the concurrent operations of your data structure or algorithm. Like for example, here shown on the slide, when we essentially want to test concurrent link deque data structure from Java util concurrent package from the standard library. Yeah, so we just need to annotate certain operations with this operation annotation, and then run the test shown on the bottom. And what does Lincheck do? Well, first it starts to generate different scenarios for your algorithm. So basically it just generates like n random threads filled with random operations, and then it executes it. Lincheck has two modes how it can execute your test. So first it can just execute it in stress test. It just essentially, it means like it will just run it multiple times and try to discover some bug. Or it can execute it in model checking mode. So the model checking mode, it's essentially like a way to systematically and deterministically generate various traces of the program, like yeah, and test each trace for certain properties. Lincheck detects different types of bugs. For example, it can detect linearizability violations, deadlocks, blocking for non-blocking data structures, and so on. So here on the slide, an example of the generated scenario is shown. So it's one of the 100 scenarios that Lincheck is going to generate for this test. And below is shown that it executed in model checking mode and it checked 10,000 different traces of this program. So after some iterations, some number of iterations, Lincheck actually detects a bug in this algorithm. And it reports that it has found some bug, and then it tries to minimize it meaning that it tries to randomly remove some operations to see if like the bug is still present. After some number of iterations, of minimization iterations, it arrives at this program shown on the slide. Sorry, this scenario. And yeah, essentially, like it's a bit, it's not obvious, but actually the problem here is that this scenario is non-linearizable, meaning that we cannot linearize all the operations from different threads in a sequence that would be correct according to the sequential semantics of the data structure. It's actually not very important for the purpose of this talk. It's just like, I mean, the definition of the linearizability. We just need to know that here Lincheck found a bug. Another nice feature of the model checking mode is that not only it can systematically and deterministically test your program, it can also, in case it discovers a bug, it can output a trace of the program. So a trace is just like a sequence of various events that occurred in the program, like events in, like, for example, read or write to shared variables or locks, unlocks, and stuff like this. Yeah. So here we can see the trace consisting of two threads, and the Lincheck shows in what sequence we need to execute this instructions, these operations to hit the bug. So it's actually very useful for testing concurrent data structures. And more than that, the people from our team recently developed a IntelliJ IDEA plugin that makes it even more convenient to work with. So essentially, you can not just look at this trace in the output, but you can open it in the IntelliJ IDEA and then step it through it with the debugger. So I have, yeah, like it has like trace view, debugger integration, and data structure visualization. I actually was going to show a quick demo how it looks like. So yeah, it's a different program, but like it doesn't matter. So yeah, yeah, basically here you can see that Lincheck has found a bug in this scenario shown on the left. Then you can also see the trace on the right bottom and the state of the data structure on the right. And you can step to this trace. You can step forward or backward. You can see how the program was executed and how it altered the state of the data structures and what get wrong. Yeah. So yeah, that's basically how the Lincheck works and how it is useful. So next, I'm going to tell more about the model checking itself. So Wikipedia says that model checking is a method for checking whether a model of the system meets a given specification. So it's very broad definition. We are going to talk about software model checking in particular, which means that it means that we take our program, we execute it in some controlled environment where we can control, for example, how threads are executed, in which order. We can intercept certain calls of the program and substitute the result, like stuff like this. Essentially, we take the program, we take the code of the source code of the program as it is, and we execute it in some controlled environment. And then partial order reduction is a special technique like it's an optimization technique for model checking of concurrent programs specifically, which aims to reduce the state space to be explored by the model checker. So essentially, like as it is now in the Lincheck, it has a pretty simple model checking algorithm. It just takes your program, starts to execute it, and whenever it encounters some shared event, like shared memory read or shared memory write or walk and walk and so forth, it inserts a switch point, and then it considers different possibilities, like how it can schedule threads in different orders. But it is apparent that often it is kind of wasteful exploration strategy because not all thread interleavings are interesting in some way. I'm gonna tell a bit more about it, but for now it's just we just need to understand that partial order reduction is a special technique that help us to reduce the search space that should be explored by the model checker. And in the essence, the main idea is that we can exploit that certain operations from different threads are commutative, which means that the order in which they appear in the trace doesn't matter. We can reorder them and the result will be the same. So I'm gonna show this on some examples. So again, going back to this concurrent deque, we can, for example, have a look at this scenario shown on the left. And yeah, basically the current model checking strategy, it just takes this scenario and explores like 10,000 different traces. And then if we'll take our prototype model checking strategy with partial order reduction, it just explores only like around 200 traces, because essentially it is all the traces that it need to explore for this program. Because if you actually have a look at this program, you will see that most of the operations are just a kind of pure operations, like pull first, pick last. I mean, sorry, they are not pure, but the point here is that we just have here only one operation that actually kind of modifies this one, add last, that would add a new node to the deck, and the other are just trying to remove this node. But it's actually like not hard to imagine that there's not a lot of interest in interleavings here. Yeah, because we just add only one new node to the deque. So like earlier or later, it's like these operations will just remove this node, and then the rest of the operations will do nothing essentially. And if we will even go further and we will consider just we'll consider a scenario where there's no insertions at all. Yeah, so the simple model checking algorithm still discovers 10,000 different traces. Like 10,000, it's not a total number, it's just a bound that we set. Yeah, but the strategy with partial order reduction, it explores just one interleaving, because like here, it doesn't matter in what order you execute these operations, because none of the operations insert anything to the deck. So all the operations will just return null, and that's all. Like there's no point to try different interleavings here. And like it's not that it is some special, there's no special optimizations for this particular data structure in the algorithm. It's just the way the partial order reduction works. It can automatically kind of deduce that in this particular scenario, there's no point to try many interleavings. Yeah, so if, by the way, yeah, if you want to ask some questions in the process, yeah, please give me some hint or something, and I can answer questions. I can take some questions in the process. Okay, so we have a prototype of this thing in a branch. It's not yet integrated into kind of the main branch of Lincheck. We are working on this, and we hope we'll finish soon. But you already can try it. It actually works on many algorithms, for example, from Java util concurrent. Yeah, so you can check how it works, and yeah. So yeah, before I'm going to explain our algorithm in detail, I want to touch on like our work. It's not that we are first who are implementing this kind of system. So there's quite well-known model checker for C programs. It was developed in Max Planck Institute by Michalis Kokonagis and Victor Refiadis and some other people. So it was kind of one of the I don't know, pioneering work in this area when like applying the partial order reduction to test concurrent programs in real languages like C. And what is more interesting, they even check for various weak memory behaviors. I'm gonna touch up on this in the end of the talk. So yeah, basically it's very good if you kind of need to test some algorithms in C or C++ to some extent, you can use this system. And there's also a similar stateless model checker also for C and C++ programs called NeetHack. It's also open source and you also can try it. And now to compare our work to prior art. So our implementation in Lincheck, it's based on similar ideas and similar concepts, but we have a slightly different algorithm. And basically the main difference is that we use a different data structure internally to represent the state space of the program. And this data structure, it's called event structure. It's kind of very old concept in computer science. And it's kind of very kind of a way to compactly represent the state space of concurrent program. And there's a lot of technical differences in our implementation versus existing implementations. So first of all, obviously the two tools that I mentioned, they are developed for C++ programs, and they are based on the LLVM stack. So they only work with programming languages that can compile to LLVM to some extent. Our system is it's developed for JVM languages like Java, Kotlin. And another kind of important technical difference is that these tools that I mentioned, they also kind of interpreter based in the sense that inside these tools, they have essentially an LLVM interpreter, custom LLVM interpreter that interprets your program in this special way. In our system, it's a bit different, is that we don't have like completely, you know, separate JVM bytecode interpreter. We just instrument the JVM program to hijack certain calls or certain events. And the rest of this code, the rest of the code that we are not primarily interested, it's just executed as usual by the JVM. I think this is kind of important difference. And as I will tell in the end of the talk, like this instrumentation-based approach, I think it's a bit more nicer when you want to kind of integrate it with just like, for example, third-party libraries, or like if you want to check only part of your code. And I will explain it later in the talk. Okay, so now going back to partial order reduction. So how does it work? So suppose we have this simple concurrent program. We have 3 threads in the beginning, like each thread writing to a variable, like first thread writing to x value 1, second thread writes to variable y value 1, third thread writes to X value 2. And then we have another thread that happens after all these 3 threads, and it just reads the state of the memory. So the simple model checker algorithm, it will just enumerate all possible interleavings of this program, all possible traces of this program. So it's 6 of them, yeah, because like this operations in free thread, they can execute in different order. Sorry. Yeah, but what we can do actually, we can notice that, for example, it doesn't matter what is the relative order between write x1 and write y1. Yeah, because no matter what, these 2 operations, they alter different memory locations. And no matter what's the order we execute them, the end result will be the same. And this is the main idea behind the partial order reduction, and says that essentially we can split all the traces of our program into equivalence classes. And then from each equivalence class, we can pick just one representative trace to check. Kind of the state-of-the-art approach now is to base this on so-called PORF equivalence. So we consider the 2 relations in our traces. The program order, it just says like it connects the events from the same thread, and it says in what order these events were executed by the program. And the reads from relation, it for each read event, it tells from which write event this read takes its value, from which it reads from. Yeah, so we can split these traces based on these 2 relations into 2 equivalence classes. And we can also draw these graphs for these equivalence classes that depict these events and this program order and reads from relationship between them. Yeah, and then we just need to, instead of like 6 traces, we just need to check 2 traces. Like basically we can pick any trace from the first class, any trace from the second class, and we can check that only them. Okay, that's good, but the question is, how do exactly we dynamically kind of build this equivalence classes, how we actually execute program with this idea in mind? And the basic idea is also kind of simple. We can apply this kind of data race reversal approach. So suppose we have this program shown on the slide. So what we can do first, we can just execute it in some arbitrary manner. Like, for example, like this. So we can execute it so that, you know, no reads, just read like initial value. And then looking at the execution graph of this trace, we can search for data races. We can pick one data race and reverse it in the sense that we change this read to read from race write. And from that, we can arrive to the next execution graph and we can check it too. And so we do this iteratively, like we take execution graph, search for data races, reverse data races, and check the new execution. Now the question is how we can like efficiently, because like obviously each execution graph can have multiple data races, and like moreover, if we start from some graph, then arrive at the next graph, how we can guarantee that we do not, you know, at some point loop back to some graph that we already considered. So we need some data structure to store all of this information during execution. And the data structure that we are using is an event structure. So like initially event structures were proposed as semantic model for concurrent programs. And like the point is that a single event structure, it encodes all of the possible events of the program and the relationship between them. So for example, here we can see an event structure for this program shown here. So what does it have? Okay, we have, again, program order and width from relationships. And then the event structure itself, it also builds upon two main relations. It's the causality order and the conflict relation. So causality order is kind of, it tells which events causally depend on which, and so forth. For our special case of this execution graphs, we just take causality order to be the union of program order and width from, and we take its transitive closure. So it's kind of transitive relation. So for example, this event E7, it depends on, causally depends on E2 and E1 events. And next is the conflict relation. It just says, like, if we have two events, it essentially says that if these two events are in conflict, they cannot belong to the same execution. They have to belong to different executions of the program. Yeah. And there's like a bunch of axioms on this causality and conflict relations. I'm not gonna give the formal definitions, but essentially we require that causality order is a partial order, and the conflict relation, it has to be consistent with respect to causal order. So what it means that the essentially like the event cannot causally depend on some conflicting event. Yeah. So if you take some event, all of its causal predecessors should not be in conflict with it. And then from this event structure, we can extract different executions of the program. So the program execution is just causally closed and conflict-free subset of events. So for example, for this program and for this event structure, we have three such subsets. So for example, E1, E2, E3, E, and E4. This subset of events, it's causally closed, meaning that if you take any event from this set, all of its predecessors also in this set, and it is conflict-free. Okay. So there is one problem with this event structure. Like here we can see that this event structure, it encodes the whole state space of the program, like all the events of the program, and it's obvious we cannot keep this whole event structure in the memory for the whole duration of our execution of this program, because like it will have like exponential number of events. Yeah, so it's not maybe not exponential, but okay, it's gonna be a lot of events. We can't keep it in memory as this. So what we do in our algorithm, we construct the event structure in a way such that we always keep in memory only a part of this event structure. So let's have a look on the example, how we do this. So we start executing this program shown on this slide. So each time we execute some instruction, like for example, we start from executing the left thread, we add the corresponding event to the event structure. So these events, they are stored in the stack data structure. Yeah, so like each time we add new event, we put it on top of the stack. And we mark it as visited or non-visited. I'll explain it later. So okay, next we execute, for example, the second thread, the read instruction. So each time we execute a read instruction, there is actually a choice, because like a read event, it can read from different write events. And if we have several write events in our current execution, it can potentially read from any of them. So we need to consider all possible options. So what we do, we add all these events, like we add all possible, like for each option, we add a separate event. We also represent this read event actually as a pair of events, like the request and response part. And request part is kind of like special artificial event. It's kind of virtual event. It's just convenient for the algorithm to represent it this way. But like logically, these two events represent one semantic event. So yeah, we add for each option to read from, we add and corresponding response event. And we pick one of them to visit at the current execution, and the rest, it stays on the stack, but it kind of means we are going to get to it later. Like we just remember that there was this option and we will consider it later. So we continue the execution, like write event, it has no options, so we just add it. And then for yeah, basically, when we add another write event here, we again add it to our current execution and to the stack. But like interesting point here is that now that we have added it to the graph, we also need to consider an option like when this read event that were already in the graph, it now can read from this new write event. So we also add it as an option to our event stack. Yes. So at this point, we finished one complete execution of this program. This execution consists of this 5 events, including one synthetic event, E2. Yeah, so we have E1, E2, E4, E5, and E6. And next, what we are going to do, we are going to look at our event stack. And from the top of the stack, we are going to find first unvisited event. So we find it and we switch to this event and we start like executing program again, but now with this event in our current execution. So like basically we don't like we re-execute the program from the start for all the events that are already in the graph. We just follow the steps and check that we match the events that actually in the graph. And then when we reach this point of E7, we continue execution. Yeah, and here it's just that we add another write event. Now, there was some question.
No, I was just coughing. Sorry.
Okay. Yes, now we generated another complete execution of this program. And now again, we have a look at our event stack, find first unvisited event, and we go back to it. And basically we remove all the events from the stack that are after this event because we no longer need them. So we get to this point, and again, from this point, we again start executing program, adding the events. And we reach the last one, the last execution of this program. So that's kind of the basic idea of the algorithm. Now, another interesting thing that we have is that another important remark is that here it actually doesn't matter, but in some cases when we add read response option for our execution, we can actually kind of read from inconsistent place, like inconsistent in the sense that it's, for example, like the resulting graph would not be sequentially consistent. For example, if we're aiming to generate only sequentially consistent graphs, we can accidentally create a read from option that is not sequentially consistent. So like each time we roll back to this to the new graph, we check that it is indeed a sequentially consistent graph. And we actually here we can substitute sequential consistency for any other consistency criteria, but for now we only implement the sequential consistency. Okay. So yeah, another interesting part that we have is that, okay, here we had this read and write events, but in general, we have in real world concurrent programs, we have different types of events and different types of synchronization rules between them. But actually, they all follow the same pattern in the sense that we have, for example, we have, let's consider locks. Yeah, for example, whenever we have some lock object, we can lock or unlock it. Yeah, and basically here the idea is the same. Like whenever we want to lock some mutex, we need to find an unlock event that released it previously, and we need to synchronize with this. So we model this pattern of synchronization through another concept called synchronization algebra. So it's just a way to write this synchronization rules in this algebraic form, like just a set of equations. And then the algorithm, it can work in this abstract way, like basically, like whenever we add an event to the graph, we don't need to like check different cases. Like if it's the write event, we need to go through all read events and so on to add various reads from options. Basically, the algorithm says like whenever we add an event, we need to go through all other events that can potentially synchronize with it according to these rules of synchronization algebra and try to synchronize. And by synchronize, meaning that we need to, we kind of check if we want, if we can create another event that represents the result of synchronization of two other events. So for example, write event that writes value alpha, it can synchronize with the read request event to the same location. And what we get in the result is a read response event with the value that was written by the write event. For the locks, we have a similar pattern. Like if we have an unlock event, it can synchronize with the lock request event and it will produce a lock response event and so on. So this is just kind of a nice way to abstract all different synchronization patterns that we have in the programs and handle them uniformly by the algorithm. Okay, I think that's all that I wanted to talk about the algorithm itself. So if there are some questions at this point, I can answer it.
Yes, I have a question. So on the slide number 21, and you said that you have the check for the consistency of the graph. And result. Yes, here on the bottom. Does this imply that in the future the model checking mode with this partial order reduction scheme will be able to work in non-sequential consistency mode, which now uses?
Yeah, that's actually was one of the motivations why we started developing new algorithm, because we wanted to support different memory models. Basically not different memory models, but kind of relaxed memory model of Java. So yeah, like later we will be able to replace this consistency check, sequential consistency check with other consistency check for some variant of Java memory model, and we will be able to check more possible behaviors. Yeah, it's actually, yeah, this is not our unique idea. That's basically the idea that was, I think first was ChNMC model checker that implemented this like memory model agnostic way of partial order reduction. Yeah, so we just apply the same idea here. Yeah.
Second small question, will this rule out the stress testing mode?
Sorry, could you repeat?
does this imply that the stress testing mode in the check will be removed? So there is no need in that for the Java memory model consistency will be checked.
Not necessarily, because a stress strategy can be useful on its own, like because it's two different ways to test the program. Like you can model check it, and it kind of has its benefits. Like it is a deterministic way to execute the program, and it's a way to systematically explore different interleavings. But there is downsides, like because essentially what you do, you not fully execute your program, like your real program. You execute your instrumented program. Like it's not the same thing, you know. It might be that you actually check something that is not fully correspond to what you will be actually executing in the real world. Yeah, because in the real world you will be executing non-instrument version of the program. So it kind of also good to check this thing too, like execute your program without no instrumentation. And another distinction is that, okay, even with partial order reduction optimization, for large enough programs, you would not be able to test all possible interleavings, because like this space, it grows very rapidly. And you only can, with model checking strategy, you can only execute part of this space, check only part of this state space of the program. And with stress strategy, you can randomly pick some other interleavings that perhaps your model checker wouldn't pick, because it wouldn't, I don't know, have capability to do so.
I see. Thank you.
Okay. And now,
Still coffee, sorry.
so next I'm going to tell a bit about the technical changes that we had. So the first technical change was that because like Lincheck was already a kind of established tool, and there was a lot of different use cases and various features that were supported, we cannot just develop a strategy that like break things that were working before. So we needed, from the start, we needed to support many things. And another part of this problem is that Java really has some non-pleasant APIs regarding memory accesses in particular. So there's like 1, 2, 4, 5 different ways to how you can write to shared memory in Java. Yeah, it's basically like true plain or volatile fields using atomic classes, using atomic field updater classes, using wire handle API, or using unsafe API. And we kind of, the bad news is that all of these are actually used in different algorithms, especially like in Java till concurrent. Like I think there are even like classes that use several APIs at the same time. It's very confusing and kind of difficult to work with when you want to build some verification tool for Java. And apart from this, we also needed to support other features of Java, like monitors, intrinsic locks, walk-on-walk wait notify operations with them, thread parking and unparking. In case of Kotlin, we also need to support Kotlin coroutine primitives. And sometimes some algorithms also use a reflection to access memory, and we also needed to support that. It's not like we currently do not have full support for reflection. We just, kind of patched the holes for the thing to work in practice. And like in future, we need a more systematic way to handle reflection, for example, because it's kind of difficult, yeah. And another technical change was that the as I said, like, for example, in GenMC and in Lincheck model checkers for C, they have this. They basically are built as interpreters for LLVM code, and like they basically just take the whole your program and just execute their interpreter. But in Java and Lincheck, we had a different approach, and it works like we just take the program and we dynamically attach a Java agent to it that instruments the bytecode of the classes. And there's for these reasons, we cannot kind of assume that we can instrument all the code, like all the classes of Java, for various reasons. Like, for example, for performance reasons, like some classes, it's better not to instrument them because like it will get your program be really slow. There's also like technical limitations of Java agents, and some classes simply cannot be instrumented, like I don't know, Java object, for example. There's no way you can instrument this class and insert your hooks there. There was another thing is that there's a feature in Lincheck called user guarantees. And in essence, it gives kind of a modular verification capabilities. So the user can declare that, like, for example, we develop some data structure that inside it uses another data structure. So like, for example, I know some hash map that uses linked list inside it for bucketing. And the user, if the user wants to check the hash map implementation, it can say that, okay, assume that the list implementation is correct and is linearizable. So please do not instrument it, do not consider interleavings of list methods, just assume they are atomic. Yeah. And yeah, and basically it means that the code of the list class would not be instrumented when we will be checking the hash map. And the other thing is that, as I said, we also have this integration with the Lincheck idea and with the with IntelliJ idea and with the debugger in particular. And when we execute the program under the debugger, the user may also want to inspect the state of the program through the debugger. So it means that when we execute some code from the debugger, like for example, the string methods, we don't need to instrument them. We just need a way to be able to read the current state of the program. So because of all of these features, we needed some way to only partially kind of be able only partially model the program that we have. And we needed some unified solution for this. And the solution, it was kind of a bit inspired by concurrent execution, I think. So the thing is that we have kind of two parts of the code, the modeled code and external code. So the modeled code is the code that we have instrumented, and in the modeled code we intercept all the events that happen there, all the read, writes, walks, and so forth. And there is external code, and external code, it is not instrumented. And although like on this picture I showed the events that happen, but kind of in the model checker we don't track these events. It's kind of, we don't have any way to see these events in the algorithm. So we need some rules for these two types of code so they will be able to interact with one another. And the invariants are as follows. So basically, the external code at any point it can read from modeled state and get some consistent state of the memory. And similarly, modeled code, it can read from external state and also get some values of variables. And the idea is that if we try kind of formalize this, so when we model check the program, we have this execution graph, as I said. And the execution graph, one execution graph, it codes a set of traces of the program. So in essence, what happens is that we can pick one trace of the program, representative trace from this set. And we can see, suppose if we were executing this trace, what state of the memory we would arrive at. So and the way we do this, we always kind of maintain the actual state of the memory according to this virtual state that we had if we executed the trace of the program that we choose. It's maybe a bit convoluted, but basically, we execute the program, we build this execution graph, but we also actually keep the state of the memory. And the state of the memory, it corresponds to the execution graph that we model. Okay. And because of this, if we have some external code, it can always read from the memory and it will get some consistent state of the memory, something like this. Okay. Yep. So do we have any questions here before I move on? Okay. Yes, so that's actually all that I wanted to tell about the algorithm and the technical challenges. So a bit of future plans that we have. So, okay, first of all, we need to finally merge this thing into the main branch of the Lincheck. It's still kind of, we're kind of, I think we are going to do this soon. There's like small technical problems and stuff like this, minor bugs, but I think we'll soon will be there. We also have kind of, yeah, basically we always want to like implement some performance optimizations because that's the thing we can always do. And basically for now, there's two main bottlenecks of this approach. The first one is the graph consistency checking is actually very expensive operation. So optimizing this part is very important. We have some ideas how we can do this. Basically, there's some heuristics that we can use so that we can reduce the size of the graph that we need to check for consistency. Like, for example, if we have some variable that doesn't have data races, we can remove all the events accessing this variable from the graph because they cannot kind of validate consistency. Or at least this is our hypothesis for now. The bytecode instrumentation is also can be a bottleneck, and there could be some ways to do things more efficiently here. Next, another big feature that we want to implement is that now that we have this cool algorithm that kind of already designed with memory model support in mind, we want to implement some abstraction of Java/Kotlin memory model, like not sequential consistency, but actual memory model. So we will be able to detect behaviors that are only can happen, for example, on ARM machines or x86 machines. And as I said, like the algorithm kind of designed with this in mind. So it's like once we finalize the algorithm, this particular task, it's would be kind of easier to get to implement. And another nice thing that with this algorithm, we can also develop new types of bug detectors, detect more bugs that we were not able to detect previously. So first of all, data races can be implemented very simply with in this algorithm. We can also detect missing volatile annotations and missing synchronization in general. Like we can spot that. We can, for example, get hints to the programmer. So like you need to insert some synchronization primitive here because otherwise you have some bug. Another kind of tricky bug that we can also now support is unsafe publication, also known as leaking this. It's like a situation when this reference can leak from the constructor of an object, and according to the Java memory model, bad things can happen if this occurs. And maybe some other bug detectors that I haven't thought about yet. Another interesting direction would be to try, at least from academic point of view, would be to try to integrate this with this symbolic execution then. And we have this nice Kex tool in our lab. So maybe it would be worth considering this direction too. So why it is kind of natural way? Because if you look closely at this partial order reduction algorithm, it kind of independent of an actual thread semantics of the threads. Like we can, so here we use like a concrete interpreter for threads, and we just get concrete values. But essentially we can do the same, but interpret the threads symbolically. And instead of concrete values in our events, we would have symbolic values. And then we can encode different constraints in the SMT formula, and perhaps we can even encode the event structure itself in SMT formula and just delegate all the work to SMT solver. I think that's very interesting direction to explore. Yes, that's basically it. So now I will be ready to answer your questions if you have any.
So besides new bugs that new model can detect, I suppose that there is a performance improvement with the new model checker. And is there any estimation of what's the performance improvement is with the new model checker?
That's actually an interesting question, and it's not trivial to measure, because the thing is that actually if you take this simple model checker that we have currently, each individual execution, like each individual run of the scenario that it will be faster than each individual execution we get in our new model checker. Because for the new model checker, we need to more instrumentation for the program. We need to maintain more state. We need to do more things. So each individual run will be actually slower. But because in the new model checker, each individual run encodes the set of traces that were exported by the simple model checker, we kind of need to take this into account. Like we need to, I don't know, maybe divide divide the time by the number of traces that this run represents or something like this. So measure the, the measure actual gain that we have, if that makes sense.
Okay, thanks.
Any other questions? Okay, then thank you, Evgeny, for the talk. It was very interesting.